In this video, we're going to talk about determinants of 2 by 2 matrices. So we're going to start out with a definition. Two vectors, v1 and v2, are positively oriented if the angle measured counterclockwise from v1 to v2 is less than 180 degrees. Otherwise, we say the vectors are negatively oriented. So here's an example. We have two vectors, v1 and v2. We can see here that the angle measured from the vector v1 to the vector v2 is definitely less than 180 degrees. So these two vectors are positively oriented, and we can think about the parallelogram that they form. And so we can say that this parallelogram is a positively oriented parallelogram because it is constructed from positively oriented vectors. Now, if we construct the following parallelogram, we can see that the angle measured counterclockwise from v1 to v2 is definitely larger than 180 degrees. These two vectors are therefore negatively oriented, and we say that the parallelogram constructed from these negatively oriented vectors is also a negatively oriented parallelogram. So we make these two definitions for positively oriented or negatively oriented in service of defining the determinant for a 2 by 2 matrix. So we're going to let A, with columns v1 and v2, be a 2 by 2 matrix. If v1 and v2 are positively oriented vectors, then the determinant of A is the area of the parallelogram formed by v1 and v2. If v1 and v2 are negatively oriented, then the determinant of A is the negative of the area of the parallelogram formed by v1 and v2. So we'll commonly write this number either as det A or the matrix with bars instead of brackets on the outside. Now, for higher dimensions, or just any n by n matrix in general, the columns will form an n-dimensional box in Rn. And we define the determinant of an n by n matrix to be the volume of that box or its negative, depending on the orientation. Now, for this class, matters like this are well beyond the scope. So instead of actually diving into how to appropriately define these things, we will develop some algebraic techniques for computing determinants in R2, and then we'll extend those techniques to spaces where we cannot visualize the geometry. So we're going to recall that the area of a parallelogram with base B and height h, as pictured below, is base times height. So to see this, we simply cut our parallelogram into two shapes. Then we slide the triangle to the right. The resulting figure is a rectangle with base B and height h. So it's easy to see that the area is base times height. There are three classes of matrices for which the determinant is easy to understand in general from this description. The easiest one, our first example, is the determinant of the identity matrix. So the determinant of the identity matrix is 1 since these two unit vectors are positively oriented at a 90-degree angle and form a square of unit area. Now, the determinant of the matrix, which interchanges E1 and E2, is -1 because it forms a square of area 1, but the vectors are flipped in their locations, causing it to be negatively oriented. Our next example is going to be a matrix formed by scaling the vectors E1 and E2. This will give us a matrix with plus or minus A, 0 for the first column, and 0 plus or minus D for the second column. And we claim that the determinant of such a matrix is the product of the entries on the diagonal. There are 4 cases to worry about, which are these 4 rectangles. We can see that the first rectangle and the fourth rectangle are positively oriented because the angle between the vector in the first column and the vector in the second column is less than 180 degrees, while the second and third rectangles are both negatively oriented. All 4 of these rectangles have area AD. So you can see the determinant of the first and the fourth is in fact the product of the scalars A, D, or minus A minus D. For the 2 in the middle that are negatively oriented, our determinant is negative AD, and you can see that if you multiply the 2 scalars together, you'll get negative AD. So the third and final class of matrices that we're interested in for this particular video is going to be the class of triangular matrices. So for 2 by 2 matrices, there are 2 types of triangular matrices: the upper triangular matrices and the lower triangular matrices. So as before, there are only 4 cases that we have to worry about. For the upper triangular matrix, we'll get 2 potential cases: the one where B is a positive number and the one where B is a negative number. For the lower triangular matrices, we also only get 2 pictures: the one on the left where C is a positive number and the one where C is a negative number. Fortunately, each of the parallelograms are positively oriented with height and base equal to 1. So this makes our computation very easy. This tells us that the determinant of the lower triangular matrix and the determinant of the upper triangular matrix is always 1. So in our next video, we'll use these 3 examples to compute determinants for 2 by 2 matrices in general.